Starting. Welcome. This session is the world record of pi calculation. We calculated 31.4 trillion digits. My name is Emma. I'm a developer advocate for Google Cloud. And
I'm Alex Yee, high performance computing specialist. Just curious, how many of you out here know me either personally or online? Or who have used the Y Cruncher in the past?
have you used Y Cruncher in the past? Okay, so
Okay, cool.
cool. Nobody. We have Dory. It's an online service to ask questions. There's a link from your app. So if you open the session, you have a link to Dory. Feel free to put your question upvote. We also have a mic for live questions. We're going to take questions later. So we announced this achievement on Pi Day this year. We calculated 31.4 trillion digits on Google Cloud. So today's talk is about, so we're going to take a brief look at the history of Pi. And then we're going to explain how we did this. And then we'll explain the technical details of Y Cruncher, the program we used itself. And later, we have a section for our future work. So let's take a look at the history of Pi and computers. So as Donald E. Knuth, the author of The Art of Computer Programming, said in his book, human progress in calculation has traditionally been measured by the number of decimal digits of pi. So humanity, as collectively, have tried to calculate as many digits of pi as possible since 2000 BC. And since the 1400s, we found an equation to calculate pi. And since then, we were able to calculate pi separate from the geometric features. And then in 1949, we used the very first electronic computer, ENIAC, to calculate pi. So they did 2,037 digits. And ever since then, we use pi as the benchmark for supercomputers. And the last record was in 2009. And the yellow, it's hard to see, but the record by Bellard was the very first record on a desktop computer. And then the previous record in 2016 was Peter Traub and Alex, and they did 22 trillion digits. And we did 31 trillion digits this year. And this is the first world record done on cloud.
So there are two forms of Pi computation, and we want to differentiate between the two. First of all, it is to compute all the digits from the start to end. So if you want to compute a trillion digits, you want to compute from 3.1415 all the way to the 1 trillion digit. This is the most commonly talked about Pi computation. It is very memory intensive because of the amount of data that's involved. The current world record is the one that we just said, 31.4 trillion digits by me and Emma. The other form of computation is to compute a small number of binary digits of pi at a specific offset n. This type is, it uses a negligible amount of memory usage, so it's embarrassingly parallel. And the current record is 10 to the 17th hexadecimal digit by Daisuke Takashi last year. This method is also used to verify the computation of the first type. Challenges to computing pi. So computing many digits of pi is extremely memory intensive. At the current record frontier, we're at 31 trillion digits. It requires hundreds of terabytes of memory to compute. Communication memory access is the bottleneck. It's so bad that computational power doesn't actually matter anymore. This latest computation that we had for 31 trillion digits actually had an 8-to-1 bottleneck on disk I/O. The sustained CPU usage averaged about 12.2%. In other words, the computation, like the amount of work to do computationally is actually negligible compared to the amount of disk I/O. So why is computing so many digits so memory intensive? This is actually quite complicated, but to oversimplify things a little bit, there's a very low computation to communication ratio. The runtime complexity, the computational work, is O n log n cubed, but the communication is actually O n log n squared. So there's only a log n ratio. By comparison, a lot of dense linear algebra stuff tend to be linear or even higher. And this is exacerbated by the memory wall. So for the past few decades, as some of you would already know, the performance gap between the CPU and memory has been increasing exponentially. And it doesn't just apply to memory, it also applies to disk. And so in this age, the only thing that matters is the disk I/O efficiency. So the graph, the picture on the right is actually a run in the middle of a sample computation. The bottom row here is the disk I/O usage, and you can see that it's completely saturated at about 3 gigs a second. And the top is the CPU usage, and it's spiky, it's not sustained, because the whole time it is waiting on the disk I/O. So challenges. PC computations. PCs are not very powerful. It's just one machine. They have a limited amount of memory, so you can't really go much more than like maybe a couple hundred gigs of memory. And so the picture on the top is actually my PC that I built in 2014. Not that impressive. So because PCs aren't very powerful, you need to run them for a very long time. And for computations as large, you actually need to use disk because you can't fit 100 terabytes of data onto a PC. And so the usage of disk to do computation is called out-of-core computing. We'll get to that later. Supercomputers, they have a different set of problems. First of all, they're expensive and they have limited access. Access tends to be limited to those who are in academia or those who work closely with them in the industry. Secondly, they're more difficult to program for. It's not just one machine, there are many machines, so you have to deal with communication, parallelism, and there's a lot of different topologies for supercomputers. Nevertheless, supercomputers can actually still run, but as of this date, there are no publicly available programs to actually do it.
And now we're going to talk about our overview of our architecture and the calculation. So as we said, this is the first record done on cloud. We calculated 10 pi trillion digits, pi times 10 times powered by 13. And we spent 121 digits. As we said, we use a program called Y-Cruncher. And we use one main compute node with 96 VCPs with 1.4 terabytes RAM. And I think one of the most interesting statistics is we read 9 petabytes of read and 8 petabytes of data. We wrote 8 petabytes of data. And the overall cost is approximately $200,000. But we have various techniques that we could have done to save cost. And also, this is the first time when our record was broken on a cloud service, any cloud service, and on SSDs. So all the past records on PCs used hard drives. And we also use the AVX512, the Intel's latest SIMD extensions, which probably saved the power consumption during the calculation. Why would you want to use cloud? Certainly, it's easier to run the program. You can run off-the-shelf program without modifying it. And it takes minutes to start a cluster. So we run 25 machines, and it takes about a minute or two to start these 25 machines. It's much faster than going to a hardware store and building your own computer. And also, it's more reliable. Cloud tend to have fewer hardware failures compared to your desktop computers. And we have mechanisms to reduce failures. And we live migrate virtual machines from one node to another in the case of maintenance, etc. And even when there is a hardware failure, what you need to do is only restart your instance. So you have shorter mean time to recover. And operations are easier too. When you take backups with your physical machine, you need to copy your entire hard drives. But on cloud, you just need to take snapshots. And everything can be done remotely. I moved from Tokyo to Seattle during the project, but I didn't have to move the physical machines, and the calculation was running in one of the data centers of Google. As we said, we had 25 machines, but one of the machines is the biggest machines, which run Y Cruncher. It has the latest Skylake processor with 96 vCPUs, 1.4 terabytes of RAM. It runs Windows Server because Y Cruncher is more optimized for Windows. And it had 30 terabytes of SSD to store the final results. And we needed 117 terabytes of disk. 170, so 70 terabytes of disk. So we added 24 additional nodes providing storage and bandwidth. And each of them has 16 vCPUs with 60 gigabytes of RAM. And they are just Linux servers and iSCSI targets. And we mounted the storage nodes from the Windows Server. When we were deciding the main compute node, there are a couple of factors. First, having more cores or faster CPUs means more computation power, so the calculation would be done in less time. And more memory means less I/O because we can buffer and bring more data at once. And we had two instance types with the biggest amount of memory. One is N1 Megamim 96 with 96 CPUs. This is two-socket Skylake system with 1.4 terabytes of RAM. And the other choice is N1 UltraMems 160 with 160 vCPUs. This is a four-socket Broadwell system with almost 4 terabytes of RAM. We decided to go with the N1 Megamim 96 because it supports AVX512. As we said, it's an extension of the Intel architecture, and it's faster than the previous generations. And also, having fewer sockets means there are fewer NUMA nodes. That means there will be less memory access overhead. So actually, N1 Megamim 96 could be as fast or maybe faster than the 160 vCP machine. So we picked the first choice. And in order to store hundreds of terabytes of data, we needed to have network-attached storage using iSCSI. So you can attach up to 64 terabytes of persistent disks to one compute engine. But we needed more. So we had to attach these disks separate from the cloud infrastructure. So this is done on the operating system level. So it's not subject to the limit. And instead of using hard drives, the standard persistent disks, we decided to go with the SSDs because nobody has tried using SSDs to calculate pi, like world record-breaking pi. And to connect these disks, we used Y Cruncher's own RAID system. The first reason is it's optimized for Y Cruncher, so it's more efficient. And the second reason is when you take snapshots, you don't have to worry about the synchronization between disks. If you set up a single huge file system, you might have to worry about the metadata of the disk. But when you have different disks, you don't have to worry about it. So I decided to use the Y Cruncher's RAID layer. And I ran benchmark with 20, 24, 32 nodes, and 24 nodes seem to perform the best. So I picked 24. It achieved 26 gigabps read and 16 gigabps write. So it's almost the network limit. There are additional tactics we use to keep the cluster up and running. And the first one is the iSCSI drives during live migrations. And of course, backups and snapshots are important for these kind of long-running computations. And we also set up monitoring. The first point is live migrations. So Google Cloud, especially Compute Engine, live migrates virtual machines from one node to another. In the case of regular infrastructure maintenance upgrades, network and power grid maintenance in the data centers, host OS and BIOS upgrades. So when we perform these kind of maintenances, we migrate the virtual machines so that we can perform these maintenance work without affecting the guest operating system. And these consist these gray areas. It's hard to see, but it's more than half of the total line migrations. And small portion is the possible hardware failures, such as the memory, this CPU network. If we see early signs of hardware failures, we also migrate virtual machines to another machine. And it usually finishes in tens of microseconds to finish move one node to another, but not for Y cruncher or this kind of memory-intensive workloads. So this is the diagram of line migrations. So first, we start to copy the memory from one node to the new node. And then when we copy most of the data, we stop the VM and move the state from the old VM to the new VM and restart the execution. And if there is any outstanding dirty pages on the old node, we continue to copy the data and finish the line migration. So the middle is the blackout period. So we completely start the VM, but the other two parts are brownouts. So we keep moving the VMs, but we still work in the another food. But the problem is memory bandwidth is almost always faster than network bandwidth. So with a typical two-socket machine, you have probably 200 gigabytes per second of memory bandwidth. That means 1600 gigabps. But the usual network is around 100 gigabits PS. And Y cruncher could rewrite 1.4 terabytes of RAM in less than 15 seconds. You will never catch up copying the data. And this diagram is memory profiling results of Y cruncher. And the average bandwidth on a one-socket machine is more than 50 gigabytes per second. So it's still faster than the network. So during the line migration, we stop the VM and copy the essential memory regions, and then restart the VM. So during the brownout process, the VMs keep running, but it just gets slower. And in this case, it took about 15 minutes to finish the line migrations. And for the record, the typical line migration is much faster. And in fact, 97% of line migration don't have the post-copy process at all. So they copy everything before they start the VM. They restart the VM. And 99.25 percentile of the duration is 660 milliseconds. So it's usually much faster. So this is how Y cruncher is an extreme workload on cloud. And the default iSCSI timeout value was too short. So during the slow brownout phase, these drives actually timed out and the connection was disconnected. So I had to increase the timeout value to 900 seconds so that these drives won't get dismounted. And backup was also an important point. So when you run Y cruncher, it always automatically saves checkpoints during calculation. And you can restart from these checkpoints when, for example, the hardware or program crashes. But these checkpoints are overwritten asynchronously each time. So if you crash during checkpointing, or if you take backups during checkpointings, these snapshots these checkpoints are not necessarily complete. So backups needs to be taken outside these windows. And we use persistent disk snapshots to store these checkpoint files. And in order to make the process more consistent, I run scripts to make the process, process automated, and manually run the script once or twice a week when the Y cruncher program was not running for checkpointing. And backups are only useful if you haven't restored from a backup. That means you don't have a backup. So I actually crashed the machines and stopped the program and made sure I was able to restore from one of the snapshots. So I practiced some disaster scenarios before actually running the main computation. And using persistent snapshots is actually best for backups. It automatically compresses and stores incremental backups. So it's really fast when you have fewer changes. For example, these are the copies of the same disk size. Each of the disks is 10 terabytes. But one generation is 1.8 terabytes, and the next generation is only 2.6 or 2 megabytes or so. And it's really fast. It sometimes takes less than 10 minutes to copy 10 terabytes of 240 terabytes of disks. And it's also cost effective. Even if you have 170 terabytes of data, it only costs $4,500 a month. It's much cheaper than the regular persistent disks. And as for monitoring, we set up both SAC drive and Datadog monitoring because we wanted to explore. And this is the actual dashboard during the calculation. So we put some CPU numbers and disk numbers, and we said alerts would go off when individual host goes down and the average CPU usage of an hour of the compute node was less than 1%. So that means Y cruncher somehow crashed or there was something wrong with the operating system. And these alerts worked really well. And I shared this dashboard with Alex, so we could independently check the progress of the calculation. So after the calculation, in hindsight, this might seem like a simple task of running a program that you downloaded from the internet for 4 months. But before we began, we didn't know that we could calculate this many number of digits with network drives or on cloud. And we didn't know that a single VM can run for 4 months under heavy load. Nobody, maybe somebody did, but we didn't know. And nobody did try the Y cruncher with network drives for these large calculations. And network drives are also able to handle these kind of heavy IOs. So these are some learnings we had. And now we know it's possible to run these kind of heavy workloads on cloud. And that's great. You can solve your own problems with cloud, not necessarily Pi.
So now I'm going to talk about Y cruncher. So we've thrown that name around a gazillion times already. Y cruncher is the program that we use to compute this thing, which I wrote over the past too long. So what is it? It's a desktop application for Windows and Linux running primarily on x86 and x64. It can compute mathematical constants to extremely high precision, billions, trillions of digits. What can it compute? Pretty much all the major constants, pi, e, golden ratio, Euler's constant. And the latest version can actually do custom formulas. So if you want to compute the square root of pi, sure, have at it. If you hate pi and you're a tau person, it will do it. Primary uses, it's mostly for benchmarking PCs. I'm a big part of the computer building and overclocking community, and so I kind of wrote this program both for myself and everyone else in the community. And so I have a whole bunch of machines at home overclocked, and yeah, I use my own software to test my own hardware. For benchmarking and for stress testing, which is the other half of enthusiast PC building. And lastly, of course, is to set records for all the constants. To date, it's set the Pi record 6 times, plus it holds the records for pretty much all the other major constants. And so the screenshot is just a simple, it's hard to see, a snapshot of the program computing 10 billion digits of pi on my computer. So history of Y-Cruncher. This thing goes back way too far. I'm not sure I should admit it, but so 2006 April, APCS high school class of my senior year. The project was to write a 4-function calculator in Java. And after that thing finished, I kept working on it. It was fun. And so over the summer, I added new features like square roots, trig functions, constants, and then I started optimizing it for performance. So I added a JNIC backend. At some point, I started to realize that some of the features were actually faster than commercially available products like Mathematica, one of which was the Euler-Mascheroni constant. And so that year, my freshman year of college, I computed 116 million digits of the Euler-Mascheroni constant for what I thought was a world record at the time. Turns out it wasn't. Someone had 2 billion digits, but they hadn't announced it yet. And so, yeah, that was kind of a letdown. But anyway, school took over. I didn't do anything in 2007 because I have schoolwork to do. But then 2008, while I was in one of my really boring lecture classes, I'm a terrible student, by the way. I wasn't really paying attention, and so I came across a new algorithm for performing large multiplication. I didn't really believe it at first, but after some analysis, I realized it actually solved a long-standing problem that prevented the existing algorithms from benefiting significantly from parallelism. And so I still didn't believe it. So I went ahead and implemented this thing. And I finally realized, oh my God, this thing is actually for real. So for that reason alone, I re-implemented everything from scratch this time natively in C. And I built a really big computer, this time to try again for this record. And so next year, sure enough, my roommate and I, we computed 14.9 billion digits of the Euler-Mascheroni constant. This time it was a world record. And that's when I officially named it Y-Cruncher, Y being the gamma symbol for the Euler-Mascheroni constant to the right. Since then, later that year, my roommate and I basically swept the constants list. Basically, because of the multiplication algorithm, what we had was essentially a cheat code that no one else had in a multiplayer online game. So it's an unfair advantage that I exploited to the maximum possible fullest extent, being somewhat of a gamer I used to be. So 2010 was when I started to add out-of-core support. So I mentioned the word out-of-core earlier. Out-of-core is the ability to use disk storage to do computation when you don't have enough memory. And so after that was added, I went ahead and computed 500 billion digits of E. That was a new world record. And then later that year, I joined up with Shigeru Kondo of Japan. And he, with his much bigger computers, basically swept the remaining constants, square root of 2, Coulomb ratio, and E, as well as pi itself, the big one, the only one that really matters. Since then, I've since left school. I don't have as much time anymore, so it's mostly been incremental improvements, minor improvements like optimizations, enhancements. It's been rewritten once. The program has been used to set 5 more pi records, and as well as most of the other constants. And during this time, I started refocusing the program towards the overclocking community, adding new features for stress testing and benchmarking and validation. And so people actually use the program for competitive benchmarking, competitive overclocking. What is it like today? Y-Cruncher is 500,000 lines of C++, no longer heavily developed because I have a job now. And I'm doing some research with cluster and supercomputing, but realistically speaking, that probably isn't going to happen given that I don't have as much time as I used to. And so to the right is the computer that I built with my roommate in 2008 to set the first set of records. So features of Y-Cruncher. First of all, it uses mostly state-of-the-art algorithms. I'm not actually going to go to talk about in detail of any of these because you can easily Google them because it would take me weeks to literally go into all the stuff. But it uses fast Fourier transforms for large multiplication, binary splitting for series summation, and Newton's method for division and square root. The program is parallelized and it is NUMA aware, so it will be able to utilize really big machines with hundreds of cores. On the micro-optimization front, it can use all the latest instruction set architecture extensions like SSE, AVX, AVX512. On the memory side, it has tons of cache and memory optimizations to tackle the memory wall. And then to get over the memory limit, as I mentioned earlier, it has out-of-core computation to use disk storage to overcome the memory limit. And lastly, which is actually more important than it sounds, is fault tolerance. One is the ability for the application to save its state so you can resume it later in the event of an interruption. That's called checkpointing. And the other one is software error detection, to detect errors that happen during the computation that are not detected by the hardware. So implementation details of Y-Cruncher. So as I said, I've been working on this thing on and off for 10 years now. It's 500,000 lines of code. I cannot go into every portion of it. I'll be here for a year. So I'm going to focus on 3 parts that are most likely of interest to the audience that's here. Namely, the out-of-core computation. How do I utilize disk for computation? How do I do checkpointing? And how do I do fault tolerance? So out-of-core computation. Motivation, not enough memory. No PC to date has 160 terabytes of RAM. And when they do in a couple of decades, your browser is going to end up using all of it anyway. So that isn't really, yeah, that's not going to help. Conceptually, use disk as memory. Each C++ object is a file on disk. And use RAM as just a cache for disk. And so all the data actually logically lives on disk. And if you want to do any computation on it, you have to manually bring it into memory, do your work, and then write it back. In other words, this is a form of manual paging. So what are the difficulties of this? Disk is very slow. A disk seek is tens of milliseconds. A cache miss to memory is on the order of 100 nanoseconds. So there's quite a few orders of magnitude there. And so you can't just take an algorithm written for memory and just put it on the disk. It's not going to, you'll be here for the rest of your life. Secondly, because of all the explicit data transfers, there's a significant amount of coding complexity. Likewise, there are separate implementations for in-memory and out-of-core. So much of the code is actually duplicated twice. It's written twice. And lastly, the last thing you need with all this complexity is something to get in the way, like the operating system. And so you have to fight it. I'll get into that in a bit. So this picture here is Sergio Kondo's computer, which he used to set the record back in 2012. Yeah, lots of hard drives, lots of red cables. This is awesome. This is amazing for a computer enthusiast like me. So fighting the operating system. 2009 was when I started implementing the out-of-core stuff. On Windows, you have to defeat the OS disk caching. If you allocate a large file on disk and then you start accessing it the way that Y-Cruncher does, Windows is going to it's going to try so hard to cache it that it will page itself out of memory. And so the whole system just freezes. Your mouse won't move, your keyboard won't respond, it just hangs there. And so the only way to save it, well, not save it, is to hit the reset button. And so after fighting this for a long time, the only way to actually solve this is to tell the Windows to get out of the way. And so in other words, do the buffering yourself, which means I have to deal with all the sector alignment, the read, modify, write, manage my own buffers, again, adding even more complexity to the program. Secondly is security zeroing. So if you allocate a 1 terabyte file on disk and you're right to the end of it, what happens in Windows is that it will actually zero the entire file from start to finish. So what should be an ON, essentially a free operation to one byte at the end of a file, ends up taking hours because you're watching the hard drive just grind through the entire file to get to the end. This is, needless to say, not acceptable from a performance standpoint. Why does the OS do it? Because the contents of the disk are going to contain deleted stuff from previous files. And so if you have like a password there that's been deleted, soft deleted, and then you allocate a large file on it without zeroing it, you can now access that data. And so it's actually a security vulnerability. And so the only way to bypass that zeroing is to obtain privilege elevation. But it took me a long time to figure out that I had to do that. 2010 was when I ported the program to Linux, and so I had to fight a different set of OS issues. In Linux, the failure cases were less egregious on Windows. At least it wouldn't hang your system and freeze it and require a hard reset. But overall, I was never able to achieve the level of performance and control as I could in Windows. For example, on Windows, I bypass the disk I/O cache by using a special flag, and it always respects it. If it doesn't, it fails the API call, and so I know. On Linux, the equivalent flag is called odirect. Sometimes the kernel will respect it, sometimes it doesn't. It might pass, but it doesn't really respect it. And so in the end, the program doesn't know. In the end, you get hit with a performance, sometimes a large performance hit. So the next topic is application checkpointing, the ability to save and resume application state. Motivations. OK, this computation took 121 days. There is no way this thing is staying up for 121 days. Things are going to crash. There might be bugs in the program. Power might go out. If you forget to disable Windows updates, that will screw you over too. I know. And so there is a very high probability that it's not going to run all the way through in one run. And so the difficulties of saving this state is that, one, there's a very complex program state. Like I said, it's 500,000 lines of C++. There is a long execution stack. There are recursive algorithms all over the place, hundreds of functions. There's no built-in mechanism in C++ to do checkpointing for you. And lastly, there's a huge data set. This computation required 160 terabytes of data. And if checkpointing means copying that data somewhere else, and your checkpoints are 5 minutes apart, you're not getting any work done. You're just copying data the whole time. And so the first thing, like the most important thing, is to actually get rid of the overhead checkpointing, which is to integrate it with the out-of-core computation. So as I mentioned before, in out-of-core computation, C++ objects are files on the disk. And so checkpointing is simply renaming the file and then write protecting it. So that's essentially zero overhead. And then secondly, it is to actually checkpoint only when the disk usage is relatively low. So while the computation needed 160 terabytes of disk, most of the time it's actually less than 50, but it's just those occasional spikes that actually hit those limits that actually cause it to be so high. And so if I strategically checkpoint when it's low, then we don't need as much backup storage to store the checkpoints. OK, checkpointing in C++. How do I do it? It's a total hack. I don't claim this is the best way, but it works, and if it ain't broken, don't fix it. So I explicitly maintain a copy of the execution stack. When I enter a function that is running in out-of-core mode, I call into the checkpointing framework, and it tells it that, OK, I'm entering a new function, a new stack frame, and so therefore I have the state separately that I can use to serialize on checkpoints. For program flow itself, I abuse fall-through switch statements. Essentially, when the program is running normally, it runs through the switch statements as if the cases weren't there. And then when you're loading from a checkpoint, the moment you start the function, you call into the framework, it tells you what to jump to, and boom, I'm here. And so it skips everything. At each case, I have to declare all the live variables in that stack frame, which is, unfortunately, it's very manual. It's very error-prone. So I spent a lot of time manually testing all this stuff. But once I had this sort of programming idiom set, it was very easy to extend it to pretty much the entire program. So the example here is the actual code from the implementation of E, slightly modified for this presentation. Some of the comments have been changed to explain the checkpointing as opposed to the algorithm itself. Fault tolerance. OK, long-running computations, as I mentioned, things are going to break. Checkpointing allows you to pause, resume, and back up. But it doesn't catch silent errors. So silent hardware errors, they are a thing. Y Cruncher has been used to set the Pi record 6 times. 4 of them have had hardware errors. 2 of those actually had silent hardware errors. And so silent hardware errors it doesn't blue screen your computer. It doesn't crash it. It doesn't quit the program. It just corrupts your data, and so it's all wrong. And so if that happens, you'll get to the end of the computation, and the digits will be wrong. And so you've wasted everything. And it can happen for a number of reasons: CPU, memory, disk controller. And so the only solution here is actually to build error detection into the software. And once you catch some errors, retry and then resume from the checkpoint. So here is an example of a typical divide and conquer algorithm. If you detect a fault on this node, just redo the whole block. No big deal. So how do I do software error detection? It's mostly on a case-by-case basis. There's generally 2 types of these: sanity checks and deterministic checks. Sanity checks are low overhead. They don't catch all errors. Deterministic checks, they tend to be more expensive, but they will catch all errors with high probability. Examples: if I want to check to see if any data is corrupted, I can hash it before and after the usage period. And if they hash the same thing, it probably hasn't been corrupted. That's a deterministic check. That's expensive. Use 2 different formulas to calculate the same constant. If the formulas are completely independent and they share no work, that will catch all. If they don't match, then it means something is wrong. So that will actually catch all errors, both hardware and software. And then we get to the more domain-specific things, like Newton's method convergence. Newton's method, for those of you who are familiar with it, involves iterating an algorithm until it converges. Well, if it doesn't converge, you know something's wrong. And so, yeah. Modular residuals. If you're doing integer arithmetic, like addition, subtraction, multiplication, you can actually keep a modulus of the large numbers over a prime number and propagate that along with these large numbers, because modular arithmetic is closed under those 3 operations. So you can do a whole bunch of large operations and then check the residuals at the end. This is deterministic, and it catches and it's relatively inexpensive. The last one is the most obscure of them. It's hard for me to explain, but it is also the most important one in the program. It is to check the coefficient sizes in a fast Fourier transform. So long story short, fast Fourier transforms are used for large multiplication. It's used for polynomial multiplication. Based on the sizes of the inputs, you can prove how large the outputs will be for each coefficient. And if anything is bigger than that, you know it's wrong. This one has pretty much 100% test coverage of a large multiplication, and which is pretty much probably 90% of the computation in the Pi computation. So what's the scope? Error detection catches 90% of the hardware errors from empirical testing, which is good, but not something that you could rely on. But on the flip side of that, it also catches software bugs, because the error detection, it doesn't distinguish between software error bugs. So what we have here is self-testing code, which allows me to be lazy. So if I'm writing something that I know is going to have 100% coverage by a higher level error detection check, I don't even bother testing it. Write it, and then let the code higher up deal with it later. And so this is an example of the program failing on an error check. So future work. As far as Y Cruncher, the program is in a steady state now. I don't really have any major future plans for it. It's just a hobby that I work on every now and then. I'll continue to make incremental improvements. And as I mentioned earlier, there's some ongoing research on scalability, like how to make this thing scale better on NUMA, on cluster computing and supercomputing. But these are, there's very little effort going into that.
And for cloud itself, we will continue to have better hardware, and we will be able to calculate more digits. We just announced an instance with 12 terabytes of RAM. That's huge. And for other types of workloads, we prove that cloud is capable of doing mathematical large-scale computations. So we plan to find and solve more compute intensive use cases.